Hi all, today we will discuss about digital signal processors, mainly TIS C6 7 4 8. So, what is the main distinction between DSP and CPU? Different design goals is one thing. So, one DSP is optimized for real-time numerical computations. So, real-time numerical computations like FIR filter, it is optimized for that. DSP is optimized for that. FIR filter, IR filter, or convolution, or matrix multiplication. It is optimized for those things. So normal CPU is general purpose computing like OS. So it is optimized for OS multitasking user apps. So for that purpose only it is designed. So DSP is speed and deterministic timing. Speed means like very fast, like gigahertz is very high in the case of DSPs compared to CPUs. So even deterministic timing means the branch prediction will not be there in the case of DSPs. In the case of CPUs, branch predictions might be there. On an average, CPU might perform well because of branch prediction, but branch prediction is not there in the case of DSP. So branch prediction means like what will be the next branch it will predict, and it will start fetching the instructions from that particular branch in the case of CPUs. But that doesn't happen in the case of DSPs. So if at all there is a branch is happening to some location, so whatever is the pipeline, that will flush out the pipeline and then fetch from the new branch location. So that's why the DSP, that's why it is deterministic in timing. So another thing is multiple operations per cycle. So like in C6 7 4 8, like multiple operations we can do in parallelly, like 80 instructions we can run in parallel. So that is nothing but very long instruction word architecture. So architectural differences, this is the architectural differences, main architectural differences, like 8 instructions we can run in parallel in the case of DSPs. So they are superscale out of order. Out of order means, so if at all there is you are in location instruction location 1, and next 4 instructions some data is needed which is not available, but fifth instructions data is available, then fifth instruction will be executed next instead of the first instruction. That is out of order execution. So that is possible in the case of CPU. That is not the case in the case of in the case of DSPs. So multiple specialized units are there, like for example .L is there, which will do additional logical operations. So these are various functionalities that are there in the case of DSP. .S is for branch and shift, .M is for multiply, and .D is for load and store operations. So few and registers are also very high in the case of DSPs. So like in the case of C6 7 4 8, like 16 registers are there in A path and 16 registers are there in B path, B data path. So total 32 registers are there, but a few general purpose registers will be used in the case of ALUs. Few general purpose registers are there in the case of CPUs. So deep pipeline and deterministic time. Deterministic time already branch predictions are not used. Deterministic timing means load store architecture is used, which we'll talk about later. Next we'll talk about. So load store architecture makes the timing deterministic, and also branch prediction is also not used. So because of which deterministic timing is achieved. So deep pipelines like 10 cycle pipelines are they used. So that's the idea. And hardware architecture. So hardware architecture means separate program and databases and so separate cache for program will be there, separate cache for data will be there. So that they can in the case of CPU is one human architecture, both program and data will be stored in the same memory. So that's one thing. And then the other thing is circular and bit reverse addressing is used in the case of is possible in the case of DSPs. So we will look at circular addressing today. So in the case of CPUs only linear addressing is possible. So that's one thing. So next is so real-time signal processing, like I told you, right, audio, video, and real-time signal processing is possible in the case of DSPs. These are DSP strengths. So deterministic and low latency execution. So that's one. Deterministic means I told you, right. The reason is branch predictions are not used, and also you use load store architecture, because of which the deterministic is the and low latency is possible. High multiply and accumulate throughput. So like for one cycle, like we can do like 8 16-bit multiplications in one cycle, like in the case of some processors. So multiply accumulate throughput is very high in the case of DSPs. So CPU strength is operating system multitasking. It is suitable for those kind of things. So broad instruction set and floating point support is also there. So in the case of C6 and DSP features is 8 functionalities are there. So I told you that L, M, S, D are the 4 functionalities that are there in A path, and the same 4 functionalities will be there in the D data path also. So 30-bit fixed and floating point support is also there, and hardware loop circular buffers are also there. Zero ordered addressing is there. So DSP we can achieve more operations per cycle for signal oriented code. Signal oriented code means like for example audio or speech. So signal oriented FIR filters, IR filters, convolution or matrix multiplication, all those things. More operations per cycle we can do in the case of DSP, which is not possible in the case of CPU. So introduction to load store architecture. So load store architecture is what is used in the case of DSPs. So what is load store architecture means? We will not do the operations in memory. So we will bring the data from the memory into the registers, and then we will do the operations on the registers. So that's how it makes deterministic and also low latency, because the registers are very fast to access because they are nearer to the CPU. So instead of doing operations on the memory, we bring the data into the register and then do the operations on the register. So load store architecture, arithmetic and logic operations are performed only on registers. Only on registers it is performed. So not directly on memory. Directly on memory we are not performing. Load store instruction bring data and from memory into the registers. Load instruction brings the data from memory into the register. So we load and bring the data into the register, and store moves the data from the register to the memory. So that's the idea. This is an load store architecture. Load, bring the data from the memory to the register, do the operation, multiply, add, whatever you want to do the operation, and then store the result back to the memory from the register. Simplifies instruction pipeline, improves parallel execution. So instruction pipeline is simplified and also parallel execution is possible. So that's the idea. So if you see here, this is the CPU architecture. So if you see D1 and D2 are connected to the memory. So those are for load and store. These two units are for load and store. This is the A data path. This is the B data path. These are the registers. Like in the case of C678, there will be 16 registers in this case and 16 registers here. This is general case C6x CPU architecture they are showing here. So 31 registers, 32 registers they are stored in A side, 32 registers in B side. So if you see here, this is connected to the memory. So load and store is possible only in the using D1 and D2 functional units only. S1 and S2 will be used for branch and shift instructions. M1 and M2 for multiply, and for add and logical instructions that we can do. So these all are connected to the A and A side registers, and so I told you that we load into the register and then register only will be doing the operation. So that's the idea. So if you see, these are connected only to the register, these are not connected to the memory. So data will be loaded by these function units into the registers, and from there these will do the operation. Like this will do shift, this will do multiply, this will do addition and logical operation like AND or all those things it will do. So that's the idea. So next is load store architecture. Separate units allow concurrent execution of load store and arithmetic units. Load and store is while load and store is efficient is separate is concurrent execution of load store and arithmetic instructions. Decoupling memory access avoids pipeline stalls. So like if at all pipeline, if you are doing directly on the memory, then sometimes the data may not be there in the memory. So if it is not there in cache, you have to go to the RAM. If not there in RAM, you have to go to hard disk. So those things will come into picture. So if you store them in register, then that thing will not come. So pipeline stalls, most of the cases we can avoid. Some cases we can't avoid because anyway we have to load the data into the register at that day load time. If at all the data is not there in the memory or cache, then again there will be stalls will be there. So predictable timing that I told you that's about thing, and compiler friendly. Now instruction set overview. So if you see here, so very long instruction for architecture is what is used in the case of C6x. Supports both fixed point and floating point instructions. So we can execute 8 instructions in parallel. So there are functional units like L1, S1 and L1, L, S, M and D are the 4 functional units. Both on the A side they will be there, on the B side they will be there. 4 plus 4, 8 functional units will be there. So like 8 instructions we can run in parallel. That's the idea. So 2 data paths. So A0 to A15, 16 registers on A side and 16 registers on the B sides will be there. So that's the idea. So next is delay slot. So delay slot means, so each instruction output will not be available in the next cycle itself. Like if you are writing add A1, A2, A3 output will be there in the next instruction in the case of add. If you do A1, multiply A1, A2, A3, the output will not be available in the next cycle, next instruction. It will be available after one cycle only. So what I meant to say is, so if you are doing add, if we do add A1 comma A2, these are the registers names, A3. So what this is doing is pseudocode. What does this mean is A3 equal to A1 plus A1 plus A2. This is what it is doing. So here the next instruction can use it immediately. Like for example, you can next, if something is there, shift is there, SHR is there, A3 comma by 3 amount, and then store it back to A3. We can use it after the this instruction. If at all this is multiplying, this will change to this thing, and this A3 will not be available immediately after 1 cycle. So here we need to put a NOP here, no operation you have to put. So after 1 cycle only it can be used. So this value, if you put it here, this SHR A3, then the previous, whatever is the previous value, whatever this new value A1 into A2 will not be available. Previous value, whatever was there, that one will be used by this. So you have to put a NOP here. That's the idea. So these are nothing but delay slots. This is what is called delay slot. So after 1 cycle only we can use the output of this thing. So that's the idea. So in the case of branch 5 delay slots will be there. So after 5 cycles only the branch will be taken. In the case of load instruction, 4 delay slots will be there. So like after 4 instructions only the output can be used. So for example, if what I mean to say is, if your load is there, LDW some star A4 plus plus some A6, this value can only be used after, so we have to put NOP 4. So after the 5th cycle only this A6 will be available. So from A4 the address, the value will load in A6. After 4 cycles, in the 5th cycle only A6 value will be available. So if you want to use it here, add A6 comma A5 comma A7 if you want to do, then this value will be available. If you do immediately after this, then old value will be used. Whatever is old value, that will be used. This one will not be there. So that's why NOP you have to put. So instead of using NOPs, means it is inefficient use of the cycles. So we will later see about software, when we discuss about software pipelining, how we can insert some other instructions in between them and try to efficiently code this without using NOPs. So that's we will see later. Dot product one function we will see, and try to code it without using NOPs. That's the idea. So delay slots is this one. So next is that's what I told you. Instructional parallelism improves instructional parallelism. So that's one thing. So if you want to use it efficiently, then you have to go for this. This is the instruction set of C6x7. So if you see here, these two instructions are for, this is for single precision add, this is double precision. DP means double precision, single precision means float. This is for double values adding. So that's the thing. So floating point instructions are also there, fixed point instructions are also there. So if you see here, as architectures have new architectures have come, new instructions have come. If you see here, C6.4 is superset of C6x. So if you see here, there is a dot product, the dot P2 is there. So what it does is, so if you see here, we are loading A4. So this will be A0 to A1. A0 is 30-bit register. A1 is a 30-bit register. So 16. So 4 values, 4 16-bit values. 16-bit here A0. So this A0 will have A0 and A1, two 16-bit values. 16 plus 16, 32. So that is A0. Similarly, A1 will have like A2 and A3, two 16-bit values in that one. Similarly, B1 will have like X0 and X1, X2 and X3, 16-bit values. So like a dot product, what it will do is, so if you see here, this one will do A0 into X0, A1 into X1, and the result will be stored in A3. Result will be stored in A2. Okay, A2. This one A2 will be stored. So add you are doing here. A2 will be stored, and similarly B2 will be stored here. So like how many we are able to do, like 1 to 2 multiplications. So like one on M1, one on A side we can do, one on B side. This is why A side we are doing. This is B side we are doing. Okay. So like here, how many you are doing A side A2, how many you are output multiplication are doing 2 multiplications. In the case of B2, how many you are doing 2 multiplications. So 4 multiplication in a single cycle is possible in the case of C6x architecture. 4 multiplication, 4 16-bit multiplications in a single cycle is possible in the case of C6x. If you go for C6x plus, if you see here, double dot product is there. So double dot product, what it does, if you see here, so this is the D0, D1. So this is one 30-bit register. This is one 30-bit register. So 4 16-bit values are there. Here 2 16-bit values are there. So one instruction, one dot product, how many multiplication it is doing? Destination is, this is 1 30-bit raised to sum 0, this is 1 30-bit raised to sum 1. So if you see here, so destination odd destination, this is sum 1 is there, this is odd destination. 2 multiplications and additions are happening. So like here 2 multiplications, here 2 multiplications. So total 4 multiplication, one double dot product is doing. So like how many? We have 2 for 2 multiplication units, right? So like 4 we are doing with one unit, another 4 with the other unit. So like total 8 multiplications, 4 16 cross 16 multiplication in each M1 unit. So like 4 plus 4, 8 max we can do per cycle. 8 max we can do per cycle in the case of C6x plus architecture. So that's the idea. So like as new architectures have come, they have increased the number of multiplications that we can do. So that's the idea. So like in the case of C6x double dot product was there, which we can do like 4 multiplications in one cycle. Now C6x plus has come, which we can do like 8 multiplication, 8 16 cross 16 multiplications in one cycle. That's the idea. Now next we will see about circular addressing. So circular addressing is like if at all we are at one location, wraparound will automatically, pointer will be wraparound in the memory. So like that's the idea. So it is commonly used in FIR filter, delay lines and ring buffers, all those things they will be used. Software checks, eliminate software checks for buffer overflows. Software doesn't check it, the hardware itself does that. So as the idea, software, so these are the registers which can be used for circular buffers. A4 to A7, B4 to B7. So these registers can be used for circular buffering addressing. So circular buffers, how it is controlled is, it is controlled by the AMR register, addressing mode register. So like if at all, so these are 2-bit mode fields will be there. 00 means linear addressing, 01 means circular addressing with BK0 will be used. 10 means circular addressing with BK1. 11 is reserved. 11 is reserved, it is not used. So BK0 we can put, BK0 is 5-bit field. 5 bits will be used for BK0 and 5 bits for BK1. So like if at all you put n in the BK0 or BK1, then like block size will be like 2 power n plus 1. So this is the block size. So if you see like, if you see here, this is the AMR register. So what is it? Addressing mode register, this one. So each of the bits have a separate level. So 0 to 5. So first 6 bits will be reserved. So next 2 bits are for the A4 mode. So what will be the case? 00 means linear addressing will be the case. If you put A4 will be used as linear addressing. 0 means circular addressing with BK0, circular addressing with BK1. So that's the idea. So say A4, 6 to 7 is for A4. And then 8 to 9 is for A5, and that's the idea. So B4 is also used here. So BK0, these are 5 bits are used for BK0. So for mode 01, and this is for mode 10. So BK1 is for mode 1. So this is also using 5 bits. So here we give n, capital N, that value we showed, right? So capital N we give. So 2 power n plus 1 is the number of buffer size. So which will wrap around. So for example, if you see here, if you see example here, so I told you, right, hardware will calculate the start address and end address. So if you see here, A4 is given, so block size -1, and then not of that we are doing, and then ANDing with this one. So if you see here, so this is the valid address is, so A4 is given here as 0x044 and BK0 is 3, so 2 power 4 is 16 bytes is the buffer address. So from where it will start? It will start from 00 to 00F. So F means 15. So 0 to 15. So F is 15. So 16 values will be the address range of this 16 bytes is this buffer size. So if you give like this also address, then also the valid range is this one. So why means, if you see this one, if you take this one, we will take, and then what you will do, this one we AND with, what we will AND? FFF, F, FFF, F, 0. Actually this is nothing but this is what? This is actually, this is how we got this is tilde block size -1. So this is what we will do, right? So in our case block size is 16. 16 minus 1 is 15. So this will come out to be, what it will come out to be, tilde f it will come. Okay, 0x, if you to put as 16 bit case, 0 0 0 0 0. So this is the case. So when you not it, whatever are zeros, they will become ones, so they will become FFF, and this will become 0. So that's what I have put here. So block size minus 1, if you see here, so this is what we are doing. Start address is calculated A4 tilde block size minus 1. That's what I have done here. So that's what you got here. So this, even if you give this address, so when if you AND it with this, all these things will come, and this will come out to be 0x80000. So this is come out to this one. So even if you have given A4 as this one, the start address is this one only. So hardware is deciding the start address. How is it deciding? This is deciding by this one. And address is decided by this, whatever is start address will get here, plus that, plus 16 bytes it will do. 16 bytes it will do. 16 bytes it will do. So which is comes out to be what, how much? And address will come out to be 80000F. That's the idea. This is the start address. This is the start. Start is this, and this is the end. So even if you give some other address also, it will calculate, the hardware will calculate like this only. So even if you give A4, if I see here, A4 I have given the like this. So A4 here I have given like this, A4 I have given like this. Even the case, both the cases, the valid address is same. So if you see here, valid address is same in both the cases. So what happens is, when address comes to this location, so next when you do plus plus, it will become F, it will become more than F, right? So that's when it will wrap around to again bring it back to 0 0. So this is what it is doing. So it will, whatever it will increment, when it crosses FFF, it will bring it back to 0 0. So it keeps on going like this. Circular buffer is that one only. Circular buffer concept is that one only. So whenever it reaches the end, it wraps around to the beginning. So that's the idea. So these are the bits that are used. So if you see here, we are doing two circular buffers. A4 is 16 byte and B4 is 64 byte. So these buffers we want to create. So how will we create? BK0 is 3. 16 means 2 power 4. So BK0 we have to give as 3. 16 bytes will come here. Value will be 16 bytes. Because 5, 2 power 5 plus 1. So 64 bytes will come. So BK4 is 01. So since we are using BK0, 01 should be given to this. And BK0, if B4 mode is 10. So if you see, AMR bits should be like this. So first 6 bits will be all zeros because they are reserved. If you see here, they are reserved. So next bit is 01. A4's value you have to give. So 01 I have given. This 01 has given. Next values are all linear addressing. A5, A6, A7 are linear addressing. Next B4 mode will come. If you see here, A4, A5, A6, A7, B4 mode will come. So B4 mode is 01. So the 01 as I have given here, 01. Before mode is 10. So 10 I have given here. So if this is for 01 is for A4, A5, A6, A7. Then this is for B4. B4 is 10. So the 10 is given. Remaining B5, B6, B7 is 00. Next one is 3 we have to give. BK0 will start, right? So first BK0 will come. So BK0 we have to give. So 110. So next 5 bytes, like these are sorry. So these 5 bytes, 110, 11 means 3. This is 3, nothing but 3. Next 5 bytes we will give as 5 we have to give. BK0 is 5, right? So 101 is 5. So that's the idea. So if you represent this thing in hexadecimal, this comes out of this. So this value has to be given to the AMR register. Then the A4 and B4 we can use as circular buffers. So that's the idea. So next we will come to hardware pipelining. So hardware pipelining, what it will this is a very long instruction word. So multiple instructions overlap in execution, improving throughput. So if you see here fetch packet n. So here entire fetch packet is parallel. So all 8 instructions are parallel. That's the assumption that we are making here. If that is not the case, so what I mean to say is, if you say here instruction 1 and then parallelly, so So instruction 2 is this one, instruction 3 is this one, instruction 4, 5, 6, 7, 8. So there is a fetch packet and execute packet concept is there. In this case, both the fetch packet and execute packet is same. So that's the idea. So here the fetch packet and execute packets both have 8 instructions. So this is 8 instructions in parallel. All our instructions are parallel. So if at all we have multiple fetch packets, for example, multiple execute packets, for example, this is there. These 3 are again parallel. So here if you see, these 3 instructions are parallel, these 3 instructions are parallel, these 2 instructions are parallel. So when we fetch a fetch packet is, we will fetch 8 instructions together. So here we are having like 3 execute packets. So this is one execute packet, this is one execute packet, and this is one execute packet. So when execute packets, when multiple execute packets are there in when a single fetch packet, what happens is we will see stalls. For example, if you see here, this is for the first execute packet, this is for second execute packet, this is for third execute packet. So the entire this thing, the after here the dispatch is coming, right? So here the pipeline stalls have come here. Entire pipeline has been stalled here. So next PR can come only here. So next this thing can come only after this dispatch is over only, then only it can come. That's the idea. So entire these entire how many instructions, like 1, 2, 2 instructions are stalls here in this case, because we had 3 execute packets in this one. So because of the 2 stalls have come in the entire pipeline. Okay, so that's the idea. So if at all everything is parallel, then there will not be any stall. That's the pipeline that you have shown here. So 8 instructions all are in parallel, there will not be any stall. If you see here, there is no stall here. And if you see this particular, this is the full pipeline. So each of these, say if you see here, this fetch is taking 4 cycles, decode is taking 2 cycles, and execute is taking 5 cycles. Okay. So like so each of these will be done by a different unit, different unit. So we can overlap these executions. So like for example, PG can be done by one hardware, FPS can be done by one hardware, PW can be done by one hardware. So everything can be done by one different hardware. So all these things can run in parallel. This is the hardware pipelining. So all these things are running in parallel. So the different stages of the different, so this is the fetch packet n, this is this thing. So if you see here at the clock cycle n, the fetch packet n is in execute phase, fetch packet n+1 is in decode phase, fetch packet n+2 is in dispatch phase, fetch packet n+3 in PR phase, fetch packet n+4 is PW phase, fetch packet n+5 is in PS phase and PG phase. Different are in different phases. So when you are executing the instructions, what happens is, so initially the first instruction might take 11 cycles. Okay. After that, every instruction, one instruction will be over. So that's the idea. So what happens is, if you see here, if at all each instruction is done independently, then how many cycles it will take? This fetch packet will take for 11 cycles. This will take 11 cycles. So like how many are there? Like for example, you will see here up to here, you will see these 3 will see, and then n+1 and n+2. So 11 cycles. If you do independently, how many will take? So 11 plus 11 plus 11. So this many cycles. So this will come to 33 cycles it will take. If you do each one independently. If you do pipelining, what will happen? Pipelining, if you do, so this first one will take 11 cycles. Next one, because it is overlapping with this, next one will take only 12 cycles. So 13 cycles, 13th cycle itself, n+2, all the instructions are done. So if you do pipelining, if pipelining is used, then what happens? This will come out to be 13 cycles. So how many cycles you have saved, you see? This is each one independently. If you do means 33 cycles, it will come out to be. If you are using pipelining, then it will be 13 cycles will be done with then 3 instructions. So first instruction, if you take only one instruction, then both are 11. Both will be 11. So pipelining will help only when multiple instructions are there. So initial first instruction only if you take, then 11 cycles it will take. Both will take 11 cycles. Multiple instructions are there, then the pipelining advantage will start kicking in. So that's the idea. That is the hardware pipelining. So if at all multiple execute packets are there, then stalls will come. So how many execute packets? 3 execute packets means 3 minus 1, 2 stalls will come. So that's the idea. So hardware pipelining is one thing. So if at all there has hazards in pipelining, like data hazards, like if one instruction depends on the result of another still in pipelines, we can solve that. I showed you, right? Like I showed you, I think. So if at all the load will be available, A6 will be available after only 4 cycles, then we can put knobs 4. If you don't want to use knobs, which is inefficient, then we have to go for software pipelining, which you will see next. So that's the idea. So that's about this. So next we will see software pipelining. So as I showed you, load store architecture. So all the values will be in the register, and then this, if you see here, this is the code that you are trying to execute. So it is nothing but dot product. Cn and Xn will do. So first Cp is this value. So first C will load, and then X will load, and then we will multiply C into X, and then get the product and add it to Y. Sigma we are doing it, add it to Y, and then so we have to do for 40 times. So we will subtract, counter will set it to 40, and then we will subtract, and then I told you that every instruction can be a conditional instruction. So when count is 0, this particular branch will not be executed. When count is not 0, this branch will be executed, and the loop will go here, and then this will run for 40 times. So that's the idea. Now we will, but this is inefficient. Why this is inefficient? Because we have to put knobs here. LDH C is there, right? C we can't use here. After 1 cycle we can't use. After 4 cycles only we can use it. So this is inefficient. This will not work. This code will not work. So to make it work, we have to do software pipelining. So what we will do is, so we will first load LDW. We will do LDW, and so for 2 values we are loading. 2 16-bit values we are loading. LDW is load word is the case. So 2 16-bit values we are loading. Then after how many cycles we can use? 1, 2, 3, 4. 5th cycle we can use it. Okay. Here we will do the multiply. MPY lower 16-bit values, MPYH higher 16-bit values. Okay. So next what you can do here is we are doing here we can do next load, right? Next load, next unrolling we are doing here. So second load we can do. DW 2 we will do. So this will come here, MPY 2, MPY H2. So what we are doing here is, we are loading 2 16-bit values, So like C0, C1 and C0 we are loading, and then we are loading even X0, X1 and X0 also we are loading. So we are MPY means C0 into X0 we are doing. This is entire, this thing is C. The entire this thing is C, that do better register. Entire this thing is X. So when we do MPY C comma X comma prod 1 when you do, so what, and MPY H C comma X comma prod 2 when you do, so this will multiply C0 into X0. This one lower values it will multiply. This one will multiply higher values, C1 into X1 it will multiply. So that's the idea. So we'll get both the products, like lower 16-bit will get here, upper 16-bit will get here. So that's the idea. That's what we are doing here. So that's the idea. So like load 2 multiplication will happen here. So like 1, 2, 3, 4. So 5th cycle we can do, the output will be available. Next even we can do for LDW 3 also we can do. Third load also we can do. LDW 3 we can do. So again you will come here, MPY 3 will come, MPYH3 will come here. So still we can do some more loads. LDW4 we can do. we are unrolling it actually. So this will come out to be MPY4, MPYH4 will come. So LDW5 we can do, LDW5 we can do, and then MPY5. This is the 5th cycle, fifth this thing, MPYH5 will do. Okay. So now what will so this is now done. So this multiply will be available after 1 cycle. So here we'll put add. This multiplication output will be available here. So here add is this thing, we can put it in S1 or S2, both we can do. So like we'll put it here. Add will come here, add, one add will come, another add for the high registers, so that one will the next add will come. Similarly for this one add will come here, this one add will come here. For this M3 add will come here, add will come here. So that's the idea. So now we have to branch, like for example, if you this is having the, if you see here, this will be like we can put these two things, we can copy, and we can copy here, 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 here. Yeah, this will be like 6, 6, 6, 6, 7, 7, this is 7, this is 8, this is 8. So if you see here, this is not needed, I think this is not needed. Entire thing will delete, because add also has come in one cycle. We are doing all the load, multiply, everything we are doing. So if you see here, this is the loop we can say here. So like from here, like 1, 2, 3, 4, 5. So here branch should come. So here one branch should come, and here we can do the subtract for this one. Subtract for 2 will come here, and then a branch for 2 will come here, branch 2 will come here. Subtract for 3 will come here, and then branch 3 will come here. So subtract for 4 will come here, and branch 4 will come here. Subtract for 5 will come here, and then branch 5 will come here, and subtract for 6 will come here, and then branch 6 will come here, and then subtract for 7 will come here. So what we are doing is this thing only. Instead of loading one half word, we are loading 2 words. LDW we are doing two 16-bit values we are loading, and then MPY and MPYH higher values we are multiplying. So add addition, this thing will do 2 adds will come, subtract this counter subtraction, and then branch. That's what we are doing here. So if you see here, so what is happening here? So if you see this particular thing, so entire in one cycle, this is the first cycle, cycle 1, cycle 2 is this, cycle 3 is this, cycle 4 is this, cycle 5 is this, cycle 6 is this, cycle 7 is this, cycle 8. From 8th cycle onwards, this is here the loop will come. So entire this thing will be like, so like branch, so addition will be there, subtraction is of the 7th unroll value, MP3 is for the 3rd value, LDW is for the 8th load. So like addition will happen for the first value, multiplication will happen for the 8th value. So that's the idea. So like this entire loop will be executed. So if you see here, that's what we are doing here. Even this one is what is they are showing here. So this is the first load, second load, the same thing that I have showed you, right? So this is the 7th. So 0 it has started. So like hours we have started from 1, I think. So the same thing will happen. So like this is the thing. So from here everything. So if you see here, so this is the first cycle. 2 loads will come. 2 loads the output. Second cycle, 1 subtract will come and 2 loads will come. 1 subtract as the output and 2 loads the output. Third cycle, second cycle, branch will come, subtract will come, load will come, load will come. So that's what they have shown. Load, subtract, branches come. 3 dots they have put. Why they have put 3 dots? The same thing is repeating. Branch, subtract, load, branch, subtract, load. So 2 dots. So 2 will be repeated. 1 it has come, 2 will be repeated. Next what will come? Branch, subtract, multiply, and then load. So that's what they have put here. Branch, subtract, load, multiply. After that the entire loop is starting from here. So this thing will run like different iterations. So like add is for the first iteration is running, multiply is for which iteration is running, third iteration is running here. So like, so when first cycle add will happen for the first first load and multiply whatever is the add, that will happen. So when the loop will come for the second time into this cycle, this entire thing, next thing the next multiply output will be ready, right? Thus at that addition it will do. Third multiply will be ready, that addition it will do. So it goes on. So this loop will be perfect. So this is what is software pipelining is. So like we are not using knobs. So LDW we are like 1, 2, 3. So like instead of putting knobs, so like what you have done here, so like knobs you are putting and then using A6 after that. Instead of putting knobs, we have unrolled the loop. So we unrolled the loop. So more instructions we have come. We have like so if you see here, this one is been unrolled for how many times? So if you see here, this one has been unrolled for 8 times it has been unrolled. And then instructions have been grouped together so that we can get a final 8 instructions in parallel. So that's how software pipelining has to be written. So these things we don't need to write. We can write the code in linear assembly. The compiler will generate the assembly. If you are not seeing any 8 instructions in parallel, then we have to tweak our linear assembly such that the 8 instructions in parallel can come, and like that we have to code our linear assembly, or we can even optimize the C code and then see the assembly generated assembly, and then see if 8 instructions are coming in parallel or not. If you see here, 8 instructions, when they come in parallel, then only these stalls will not be there. If at all execute packet is having multiple, like if it was showed you, right, like if a fetch packet 8 instructions, if it is having 2, 3 execute packets, then if you see 2 stalls are coming here. If at all 8 instructions are in parallel, then only there will not be any stalls. So that should be our target. So we have to check the assembly, that is generated assembly by the compiler, and then decide on that. So this is about software pipelining. So that's all about this. Thank you very much.